Welcome back as we continue plowing through section 1.3. Let's start talking about the span of a list of vectors. So given a list of vectors, the span of that list is the set of all linear combinations of the list of vectors. And we have a weird edge case where if you have the empty list, just these empty parentheses means a list of 0 vectors. The span of that is just the set that contains only the 0 vector. So, as a quick example, what we were talking about with example 2 here, where there's all of these points that we labeled, those are part of the span of u and v, because this was only allowing for integers. But when we talk about the span of u and v, we could write it like this. We could write it as the set of vectors of the form tu plus rv such that t and r are any real numbers. So not just integers. So that includes like the point 2, 2, because that was actually 0.4 u plus 1.2 v. And you can maybe imagine that any old point in R2, like let's say we take this point over here, there's going to be some way you can write that as some multiple of v plus some multiple of u to get there. Or something over here we could say is this multiple of u plus some multiple of v to get over here. So any point in R2 can be written as a linear combination of this. So the span is going to be all such points like this. That's actually going to be all of R2. So in this case, with these two vectors, the span of u and v is R2 itself, the whole thing. Let's look at another example, example 4 here. So here we have a different u and v. U is 3, 1, and v is -6, -2. And you might have noticed something about these. You might have noticed that v is actually -2 times u. Let's see how that affects things. When we graph the span of u and v, that's going to include v itself, because that is 0u plus 1v. It will also include u itself, because that's 1u plus 0v. It also includes the origin, because that is 0u plus 0v. It includes like pi times u, which is going to be like the same idea as u, but like 3.14 times longer. About here, I guess. And you could do u plus v. If you do u plus v, like drawing a copy of v, but starting at u and going backwards, that's actually just going to take you right here. You're still on the same line. So you can't get away from this line by adding u or v, because you're just like moving in a direction parallel to the line when you do that. So yeah, the whole line is the span of u and v. Any point on the line can be written as a linear combination of u and v. Okay, let's look at B. How many vectors are in the list uv? This question is making sure you understand the notation here. It's not really any math to do, but this is a list of 2 vectors. There's 2 of them. There's u and there's v. 1, 2. Okay. How many vectors are in the span of u and v? Well, that includes all the vectors that we're talking about, like 0 and u and pi times u and v and u plus v and v plus 7 times u, all kinds of things like that. Any point on this line you can scale u and or v to get to that point. So there's an infinite number of those points. How about D? Is the span of u equal to R2? Well, you might say R2 has an infinite number of points, and the span of u and v we just showed has an infinite number of points. So infinity equals infinity, right? Well, no. They both have an infinite number of points, but are there points in R2 that are not on this line here? Sure, there are. Like this point over here, which is like negative 5, 4 or something. There's no way to get negative 5, 4 as a multiple of u and or v. Let's look at E. For what values of k is the vector k5 in the span of u and v? Well, we could try to get an idea of this by looking at the graph. So, any point of the form k5 is going to be somewhere on a line that goes horizontally from here. So yeah, it looks like the span is going to intersect this somewhere out here, but it's hard to tell from the graph where that is. So we're going to have to use some linear algebra to figure this out. So another way to phrase this question is like so. We can ask, for what values of k make it so that this equation, this vector equation, has an x1, x2 solution? I think my grammar's off. This should be just what values of k make it so this vector equation has a solution. Having a solution means that like there exist weights x1 and x2 that will get you to k5. Vectors that are in the span are any linear combinations of those two vectors, right? And if we can get an x1, x2 solution, that means we can get to the vector k5 within the span. So we're going to do the same trick as before, use the definition of scalar multiplication and addition to write the vector on the left of this equation as 3x1 and x1, but then added to the negative 6x2, negative 2x2 vector. We want this linear combination on the left to be equal to k5. And as we saw before, these two vectors being equal is equivalent to the system of equations 3x1 minus 6x2 equals k as the first equation, and then x1 minus 2x2 equals 5. And that system of equations we know we can write as an augmented matrix. And then we can do some row reduction to get the solution of this. Maybe we can start by swapping the two rows, then do a row replacement operation, or multata placement. I'm forgetting my own names for the things, to clear away this 3 here. So doing negative 3 times the first row plus the second row gives you a 0. Also negative 3 times 2 plus negative 6 gives you 0 here. And then we do negative 3 times 5 plus k. That is k minus 15. Okay, now where does this have pivot positions? If we can use the existence and uniqueness basics theorem 1.2. Well, there's definitely a leading entry here. So where the 3 is in the original matrix is a pivot position. Also, this is maybe a pivot position. It depends on what k is, right? So if this entry here, k minus 15, is not 0, then it means we have like a 0 equals non-zero equation. And that means we have a pivot position in the rightmost column, and the theorem says that makes the system inconsistent. So let's write that out. But if k minus 15 is equal to 0, then the system is consistent. And we can get solutions like x1 and x2 to make linear combinations of u and v to see how we can get k5 as a result. So the way to do that is if k is 15. So if k equals 15, the system is equivalent to 1, negative 2, 5, 0, 0, 0 here. And that equation we can write as x1 minus 2x2 equals 5. And this is going to have an infinite number of solutions. We can solve for x1 in terms of the free variable x2. One example of a solution would be if x2 is 0, x1 will be 5. Likewise, if x2 is 1, then x1 will be 7. So just to check, we can do 5 times 3, 1 plus 0 times negative 6, negative 2 and get 15, 5 as a result. That was the goal. This is a vector in the span of u and v. So yeah, for what values of k make it have a solution? The answer is k equals 15. Okay. Let's think. How many solutions does x1u plus x2v equals 0 have? Well, we can do the same thing we just did, rewriting this as x1 times 3, 1 plus x2 times negative 6, negative 2 equals the 0 vector. We can apply the definition of scalar multiplication and say the vector on the left is 3x1, 1x1, and we're adding that to the vector on the right, which is negative 6x2, negative 2x2. We want that to be equal to the vector 0, 0. And the only time these vectors are equal is when the two components are simultaneously equal. And we can write the augmented matrix for this. And we can do the same kinds of row operations we were doing before to get a row equivalent augmented matrix that is in reduced row echelon form and will tell us the solutions. But actually we can save a little bit of work, because if we already did this work here, well, like the coefficient parts of this are the same as what we had before. And to get that into reduced echelon form, we would do the same row operations that we just did. The only difference is, instead of dealing with a 5 and k here, we just have 0 and 0 to deal with. But adding like switching the place of the 0 and 0, or adding multiples of 0 to 0, it's not going to change any of it. So we could maybe just like skip all these steps and just say, I know it's going to be the same as this result but with zeros over here. Okay, and there it is in reduced echelon form. According to theorem 1.2, there's no pivots over here, so it's consistent. And what else does theorem 1.2 tell us about the pivots over here? We have one pivot column in the coefficient and one non-pivot column. That one non-pivot column, the theorem says, means you're going to have an infinite number of solutions. And we could go through the same sorts of steps like we did here to actually list some of the solutions, if you want. So we wrote all the variables in terms of the free variable x2. Any choice of x2, like x2 could be 0 or 1 or 2, those will give you a different x1, x2 solution. All right. So looking at example 5, we want to show the span of u and v here is equal to R2. So in other words, we want to show that every R2 vector, which has some y1, y2 components, can be written in the form of a vector in the span. Everything in R2 can be written as something in the span. So in other words, we want to show that no matter what y1, y2 is, this equation has a solution. So we're going to go through the same steps as we did before. U is really 2, -1, and V is really 4, 1. And we know that this linear combination by definition is 2x1, -x1, that vector added to the vector 4x2, 1x2. We want to make this equal to y1, y2. And that is equivalent to the system of linear equations. Scooch this over to make some room. 2x1 plus 4x2 equals y1. Like so. And that system of linear equations has an augmented matrix like so, and we can do some row operations to try to simplify this. So first, it's nice to have something with a coefficient of 1 in the top left position without having to deal with fractions. So I'm just going to swap the two rows, and the y1 and y2 get swapped with those. And then we can clear away this 2 by doing 2 times row 1 plus row 2. So 2 times -1 plus 2 is 0. 2 times 1 plus 4 is 6. 2 times y2 plus y1 is that. At this point, we can see where the pivot positions are. It's not exactly in reduced echelon form, but we could multiply the first one by 1/6, and you're going to get some fraction here, and scale the first one by 1, and then subtract the second row from that, and you're going to have this, and then some ugly fractions over here. And the reason I'm not bothering to do that is because it doesn't really matter what's on the right sides of these equations. This is now in reduced echelon form, so we can see where the pivot positions are in the original matrix. We can see that there's one in every column of the coefficient matrix, and there is no pivot in the rightmost column. There can't be a pivot in the rightmost column because each row can only have one pivot, and all the entries are over here. So it doesn't matter what y1 and y2 is. So theorem 1.2, part 1, says that this system is consistent. And by the system, I really mean the vector equation, which we translated into a system. So in other words, every vector, every y1, y2 vector is in the span. You can write that y1, y2 vector as some linear combination. All right, let's look at part B. How many solutions does x1u plus x2v equals 0 have? This is pretty similar to what we just did. Like, we're talking about this kind of equation here. So I'm just going to rewrite that equation, but the difference is we have 0 and 0 here now. And so everything we did before in part A still pretty much applies to this. It's just that instead of y1 and y2, we're talking about 0. So I'm going to skip some steps just to say that this is equivalent to the augmented matrix with a column of zeros on the right. And yeah, we already found where the pivots were because we can do some row operations to get that this is row equivalent to 1, 0, 0, 1. And so here are the pivots. And by the way, the row operations that we do to reduce this, we're just like moving the zeros around or adding a multiple of 1 0 to another 0. So these are still going to stay zeros. So yeah, this is now equivalent to just x1 plus 0 x2 equals 0. And the second equation here says 0 x1 plus 1 x2 equals 0, which just means we have the one solution, 0, 0, which we could have seen that it has only one solution also because there are no free variables. So how many solutions does this have? 1. Sounds like a good time for a break. Let's look at example 6 in the next video.